My dear students, welcome back to our channel. In this video, I will be explaining the BCA 5th semester subject Unix programming as prescribed by Osmania University and other universities of Telangana. We will go through the important questions and answers one by one. Let's begin with a quick revision. Unit 2 first important short question is: write about daemon process. A daemon process in Unix is a background process that runs continuously without any user directly controlling it. It usually starts when the system boots and stops only when the system shuts down. You can think of a daemon like a watchman in an apartment. He works silently in the background, doing important tasks, even when people are not around. Features of a daemon process: runs in background, has no terminal or keyboard attached, starts automatically, provides important services, uses low system resources. Examples of daemons: cron daemon runs scheduled tasks, HTTPD web server, SSHD allows remote login, syslogged manages logging. Real-life example: when you schedule a job using cron tab, the cron daemon wakes up every minute, checks the schedule, and runs your task automatically. Easy way to remember: daemons is equal to always running background helpers. They make Unix stable, automated, and powerful. Next important short question is: 2. What is a semaphore? A semaphore in Unix is a special locking tool used to control access to a shared resource. In simple words, it helps multiple processes use a common resource without fighting or clashing. You can think of a semaphore like a traffic signal. When the signal is green, cars move. When it is red, they stop. Similarly, a semaphore allows a process to enter a shared area or makes it wait. Why do we use semaphores? To avoid race conditions. To protect shared memory, files, or critical sections. To allow only a limited number of processes at a time. Types of semaphores: 1. Binary semaphore, only 0 or 1, like a lock. 2. Counting semaphore, keeps count of available resources. Simple example: if a printer can be used by only one process, a semaphore ensures only one process accesses it at a time. Others must wait. Easy way to remember: semaphore is equal to traffic signal for processes. Next important short question is: 3. What are pipes? What are its limitations? A pipe in Unix is a simple method used to send data from one process to another. It acts like a tunnel that carries output from one command and gives it as input to another. You can imagine a pipe like passing water through a rubber tube from one bucket to another. Similarly, Unix pipes pass data between programs. Example: ls vertical bar grep txt. Here, the output of ls is sent through a pipe to grep, which filters only .txt files. Limitations of pipes: 1. One-way communication only. Data flows only in one direction. Process A, process B. 2. Works only between related processes, usually between parent and child processes. 3. Temporary communication. Pipes exist only until the processes finish. 4. Cannot store large data. Pipes have a small buffer. If full, processes wait. 5. No naming for normal pipes. Anonymous pipes have no name, cannot be accessed by unrelated processes. Easy way to remember: pipe is equal to one-way tunnel for sending data between commands. Next important short question is: 4. Namespaces. A namespace in Unix Linux is a feature that helps isolate resources for different processes. It ensures that one process cannot see or affect what another process is using. You can think of namespaces like separate classrooms in a school. Each class has its own students, timetable, and teacher, even though the school is the same. Why are namespaces important? They create many virtual environments where processes get their own files, their own network, their own processes, their own users. This is why namespaces are used to build containers like Docker. Types of namespaces. PID namespace separate process IDs. Net namespace separate network interfaces. MNT namespace separate file system mounts. User namespace different user IDs. UTS namespace different hostname. Example. Two containers can have a process with PID 1, but they are completely separate because namespaces isolate them. Easy way to remember. Namespaces is equal to separate worlds for each process. Next important short question is 5. Write about message queues. A message queue in Unix is a method of interprocess communication, IPC, that allows processes to send and receive messages in an organized way. Think of it like a post office box. One process drops a message, and another process picks it up whenever it is ready. Why message queues? They allow communication between unrelated processes. Messages are stored until the receiver reads them. They support priorities. Important messages can be read first. They avoid confusion that happens when using pipes. How it works. 1. One process sends a message into the queue. 2. Another process reads, receives it. 3. Queue stores messages even if receiver is not active. Simple example. A ticket booking application can send a message like new ticket booked to a message queue, and another process reads it to update the database. Easy way to remember. Message queue is equal to post box for processes to exchange messages safely. Next important short question is 6. Discuss about streams. In Unix, a stream is simply a flow of data between a program and a file, device, or another program. You can imagine a stream like water flowing through a pipe. Data flows similarly from one end to another. Unix uses 3 standard streams for every program. 1 standard input, STDIN, used to give input to a program, usually comes from the keyboard. File descriptor, 0. Example. Cat. You type input, cat reads it from STDIN. To standard output, STOUT, displays the program's normal result, usually shown on the screen. File descriptor, 1. Example. Echo hello. Output goes to STOUT. 3. Standard error, stder, shows error messages, separate from normal output. File descriptor, 2. Example. If a file doesn't exist, cat nofile.txt, error comes through stder. Easy way to remember. STDIN is equal to input, STOUT is equal to output, stder is equal to error. Streams make data handling simple and consistent in Unix. Next unit 2. Long questions. First important long question is explain process control in Unix. How are processes created, managed, and terminated? In Unix, process control means creating processes, running them, managing their behavior, and finally ending them. A process is simply a program that is currently running in memory. You can think of processes like workers in a company. Each worker has a job, an ID, and specific tasks. 1. Process creation. Processes in Unix are created mainly using two system calls. A fork creates a duplicate of the current process. The original process is called parent and the new one is called child. Both run the same code but have different process IDs, PID. Example: a parent process creates a child to handle tasks like printing, calculations, etc. B executive family used by the child process to run a new program. Replaces child's code with a new program like running ls, date, etc. Remember, fork creates a process. Executive changes the program inside that process. 2. Process management. Unix manages processes using A. PS shows running processes. B. Top shows real-time CPU memory usage. C. Scheduling. Kernel decides which process runs first using CPU scheduling. D. Signals. Special messages sent to processes. Example: sig stop pause, sig cont continue, sig kill force stop. E. Priority, nice values. Higher priority processes get more CPU time. You can adjust priority using nice renice. 3. Process termination. A process can end in two ways. A. Normal termination. The program finishes by itself. Uses exit to return status to the OS. B. Forced termination. Using signals like kill -9 PID. If a process is stuck or misbehaving. When a process ends, the parent collects its exit status using wait. Wait PID. This prevents zombie processes, which are processes that finished but still occupy space. Easy way to remember. Fork create a child. Executive load a new program. Wait parent waits for child. Kill stop a process. PS stop manage processes. Unix process control is powerful, safe, and efficient, making Unix stable for servers, applications, and multitasking environments. Next important long question is: 2. Define signal. Explain different methods to handle signals. A signal in Unix is a small message sent to a process to tell it that something has happened. It is like a notification or alert. For example, when you press Ctrl+C, the terminal sends a signal to stop the running program. What is a signal? A signal is a software interrupt that informs a process about an event. Examples of events: user pressing keys, a child process finishing, timer expiration, errors like divide by 0, request to stop or restart a process. Each signal has a name, number, and default action. Common signals: SIGINT, Ctrl+C, interrupt program. SIGKILL force kill. SIGTERM request to terminate. SIGSTOP pause. SIGCONT continue. SIGCHILD child process finished. Methods to handle signals. Unix provides 3 main ways to handle signals. 1. Default action. If you don't handle a signal, Unix performs its default action. Default actions include: terminate the process, stop the process, ignore the signal. Example: SIGKILL always kills the process, cannot be changed. To ignore the signal. A process can choose to ignore some signals. Example: servers sometimes ignore SIGINT so that they don't stop if someone accidentally presses Ctrl+C. Signal, SIGINT, SIG_IGN. Custom signal handler, user-defined function. This is the most powerful method. You can write your own function that runs when a signal arrives. Void handler, int signum. Printf, signal received, %d\n signum. Signal, SIGINT, handler. Now pressing Ctrl+C will print a message instead of stopping the program. This is useful for cleaning files, closing network connections, saving progress before exit, logging events. Advanced Signal Handling SIGAction is safer and more powerful than Signal. It allows blocking signals, getting extra information, handling multiple signals reliably used mostly in system programming. Easy memory trick. Signals is equal to alerts for processes. Handled by default. Ignore. Custom handler. Signals make Unix responsive, secure, and interactive. Next important long question is 3. What is interprocess communication? Explain different approaches to interprocess communication. Interprocess communication, IPC, in Unix means methods that allow processes to exchange data with each other. Since processes run independently, IPC acts like a bridge that helps them communicate. Think of IPC like students in a classroom. Some talk directly. Some pass notes. Some use signals. Some share a notebook. Similarly, Unix processes talk using different IPC methods. Why do we need IPC? To share data. To coordinate tasks. To avoid race conditions. To send messages or signals. To run client-server applications. Different approaches to IPC. Below are the major IPC mechanisms used in Unix. Pipes. A pipe is a one-way communication channel. Data flows like water in a pipe. Example. ls vertical bar grep txt. Parent and child processes commonly use pipes. FIFOs, named pipes. Similar to pipes but have a name in the file system. Unrelated processes can communicate. Example, nkFIFO mypipe. Message queues. Work like a post office box. Processes send and receive messages with priorities. Good for client-server systems. Shared memory. Fastest IPC method. Multiple processes share the same memory area. Example use. Banking systems. Real-time sensors. Needs semaphores for safety. Semaphores. Used for locking and synchronization. They prevent two processes from accessing the same resource at the same time. Example. Printer access control. Signals. Used for simple notifications like stop, continue, kill. Alarm example. Pressing Ctrl+C sends SIGINT. Sockets. Used for network communication between processes on same machine. Different machines example. Web servers, chat applications. Easy way to remember IPC methods. PFMSSS pipes, FIFO, message queues, shared memory, semaphores, signals, sockets. IPC makes Unix powerful by enabling teamwork between processes. Next important long question is 4. Discuss file and record locking mechanisms to Unix. How do they differ from each other? In Unix, locking mechanisms are used to prevent multiple processes from modifying the same file or data at the same time. This avoids data corruption and race conditions, like two people writing in the same notebook at once. 1. File locking. File locking locks the entire file so that only one process can read-write at a time. Simple to use. Protects the whole file. Example. A database file can be locked while one process updates it, flock, fd, lock_x, exclusive lock. Perform write operation flock, FD, lock_n unlock. Lock_x exclusive lock, write. Lock_sh shared lock, read. Limitation. Other parts of the file remain locked, even if a process only needs a small section. 2. Record locking, byte level locking. Record locking locks only a part of the file, a specific record or range of bytes. More flexible. Allows multiple processes to work on different records simultaneously. Example. If a payroll file has 100 employee records, one process can update employee 10 while another updates employee 20. System calls. FCNTL, used for record locking struct flock lock. Lock.l_type is equal to f_wrlck, write lock.l_once is equal to seek_sit, lock.l_start is equal to 100, starting byte lock.l_lay is equal to 50, length to lock fcntl, fd, f_setlk, and lock. Differences between file and record locking. Feature file locking, record locking. Scope entire file, part of file, specific. Bytes records. Flexibility low high. Multiple. Processes other processes wait. For entire file other processes can access. Unlocked parts. System call flock, FCNTL. Easy way to remember. File locking is equal to lock the whole notebook. Record locking is equal to lock only one page or line. Both methods ensure data safety in Unix multitasking environments, preventing corruption while multiple processes run. Next important long question is 5. Define FIFO. Discuss how it is useful in IPC. A FIFO in Unix stands for first in, first out. It is a special type of named pipe that allows interprocess communication, IPC, between unrelated processes. The name FIFO comes from the way data is handled. The first data written is the first data read, just like a queue in a ticket counter. Why FIFO is useful in IPC? Unlike regular pipes, FIFOs 1. Have a name in the file system, unrelated processes can use them. 2. Enable one-way communication, data flows in one direction. 3. Work like a queue, maintains the order of messages. 4. Allow synchronization, sender waits if buffer is full, receiver waits if buffer is empty. This makes FIFOs ideal for client-server programs, log collection, or task scheduling, where multiple processes need to exchange information safely and in order. How to create and use a FIFO? 1. Create FIFO using mkFIFO. mkFIFO myFIFO. 2. Write data to FIFO, sender process. Echo hello process B myFIFO. 3. Read data from FIFO, receiver process. Cat myFIFO. The first message sent will be the first message received. Example scenario. Suppose we have a chat application where Process A sends messages to Process B through a FIFO. Process B reads messages in the same order they were sent. Even if Process B starts later, it can still read messages because FIFO is named and exists in the file system. Easy way to remember. FIFO is equal to named pipe plus Q is equal to first message in, first message out. Key points. Works between unrelated processes. Preserves message order. Useful for client-server communication, logging, and task pipelines. FIFOs make Unix IPC organized, safe, and predictable, bridging communication between processes that don't share a parent-child relationship. Next important long question is 6. Explain the structure and working of shared memory. How does it help in IPC? Shared memory is a method of interprocess communication, IPC, in Unix where two or more processes share a common area in RAM. This allows processes to read and write data directly, making it the fastest IPC method. You can think of it like two friends sharing the same notebook. Whatever one writes, the other can immediately read. Structure of shared memory. Shared memory consists of 1. Memory segment, a block of RAM allocated by the OS. 2. Key unique identifier for the shared memory segment. 3. Size, amount of memory allocated. 4. Permissions, who can read-write. System calls used. Shmget, create or access a shared memory segment. Shmut, attach the shared memory to a process's address space. SHMDT, detach from process. SHMCTL, control operations like delete or check status. How shared memory works. 1. Process A creates shared memory. int shmid is equal to shmget, key, size, 0666 vertical bar IPC underscore create. 2. Process A attaches memory. Char asterisk data is equal to char asterisk shmut shmid null 0. 3. Process B attaches the same memory using the same key. 4. Both processes read-write directly. Example, a producer writes data into shared memory, a consumer reads it immediately. Advantages for IPC. Fastest method, no copying between kernel and user space. Flexible, any amount of data can be shared. Works for unrelated processes as long as they know the key. Important note. Since multiple processes access the memory at the same time, synchronization is needed using semaphores to avoid conflicts. Easy way to remember. Shared memory is equal to common RAM notebook for multiple processes. Fast. Direct access. Needs semaphores for safety. Shared memory is ideal for real-time applications, large data exchange, and high-performance IPC in Unix systems.